in PODEM algorithm, so the basic idea is that instead of this J frontier of this D algorithm, so we take it to the primary inputs. So, for a particular point to be justified, we figure out the primary inputs that are responsible, that can control the value at that point, and then try to set the primary input to some appropriate value. So, for example, in this particular circuit, so the target fault is f stuck at 0. So, first objective will be to set f to be equal to 1. So, that to achieve the target fault, the f should be, the line f should be set to equal to 1. So, if we backtrace from this point, so we come to the point C. So, it generates the backtrace routine. So, it generates the another objective, which is C to be set to be equal to 0. So, since it is a primary input, so it can be easily set to 0. Now, we simulate the case C equal to 0. So, when C equal to 0 is simulated, then this D frontier becomes this line G. The D frontier can proceed to G, and some gates have been assigned, like as we are simulating C to 0. So, C, D, E, H, all these lines, they get the value 0, and the line F, it gets the value D. Now, we have to advance this D frontier further. That is the second objective that comes up. We have to advance D frontier further. So, if we want to progress this D frontier from F to G, I have to set the corresponding objective that comes up is setting A equal to 1. Now, we backtrace from the object. So, A equal to 1. This is nothing to be backtraced. So, we just simulate for A equal to 0. So, simulate A equal to 1, it simulate for A equal to 0, and this will make it this line to progress. Okay. So, sorry, this should be A equal to 1, simulate for A equal to 1, and then that will propagate this F to G and that G to Z. So, that way fault will get detected at Z. Another example that we can look into is that we target that B stuck at 0. So, to excite the fault, we have to have B equal to 1, that is the first objective. So, if we backtrace, we get A equal to 0 to be the objective. Now, you simulate for the event A equal to 0. Now, we see that B becomes equal to D, because that is the point to be for the fault has to be traced, and then since A equal to 0, C becomes equal to 0 and D becomes equal to 0. So, D frontier becomes empty. So, we have to backtrack. We backtrack. Now, we have tried with A equal to 0 decision. We backtrack and try to consider A equal to 1 decision. Now, if we simulate for A equal to 1, then also B becomes equal to 0, C equal to 1, D equal to 1, and the D frontier still empty. D frontier vanishes in fact. So, we see that there is no more backtracking that can be done. So, this fault becomes untestable. So, that is the operation of the PODEM algorithm. An improvement of PODEM algorithm is the fan algorithm. So, what it does is that it extends PODEM algorithm. So, there is a concept of headline. So, headline is that whenever we come to a point where we come to a fan out free cone, so that is called a headline. So, that is one advancement we do, because if we have got a combinational cone, that means all those output can easily be satisfied. Like if I have got say a cone like this, then to get a value at this point, since it is a combinational logic, so it is very much possible that I will be able to set these primary inputs to some value, so that either 0 or 1, whatever we are looking for, can be set at this point. So, that means if we have reached this particular point in this entire circuit, when we are backtracing, so if we reach this particular point, so there is no necessity to trace back and try to justify at the primary input, knowing fully well that this part can easily be done and there exists a solution for this part. So, that is once we reach this headline, we do not need to backtrack further. Another thing is that multiple objectives will be pursued simultaneously, because what happens is that if we pursue with one objective, so it sets some of the primary input to some value. Later on, we have to pursue some other objective, and that may give rise to conflict. So, if we can pursue more than one objective simultaneously, then possibility of conflicts are less. So, these two are the extensions in the fan algorithm compared to PODEM. So, as I was telling, that headline, so output signals of fan out free cones, like in this particular circuit. So, this point x is a headline, point y is also a headline, because they are the output of this particular fan out cone. So, x fan out cone is consisting of these nodes A, B, C and D primary inputs, and y's fan out fan in cone consists of E, F, G and H. So, this all these fan out free cones. So, this is a fan out free cone. So, there we have got the headline. Any value on headlines can always be justified by the primary input, since it is a combinational logic. So, it must be justifiable, otherwise this is only the reverse, or the non justification can occur only if the circuit is not designed properly. But assuming that when we are going to the testing phase, the circuit has been circuit is well designed. So, naturally we can always find some primary input combination which will make the headline point to be true or false as per our requirement. So, if we are doing some fault test pattern generation, then we can for example, if we are trying to generate some test pattern for Z. So, once we come to the points x and y, we know that rest of the thing can be done easily. So, we can reduce the number of back traces to the headlines only. So, you do not need to go further. Multiple objectives, like in this particular case, suppose we have got two objectives, k is to be set equal to 0 and m to be set equal to 1. So, these are the two objectives. So, if we proceed with one objective at a time, for example, if we try with k equal to 0, this objective has to be satisfied. So, if we come back, maybe we will choose b to be equal to 0, though there are other options by going through the inputs of these OR gates and all that. But suppose the algorithm picks up the b input first and it justifies k equal to 0 by setting b equal to 0. But when we simulate b equal to 0, we see that this m becomes equal to 0. So, there gives rise to a conflict. So, it conflicts, it violates the second objective m equal to 1. So, we have to make the backtrace algorithm more intelligent, so that these future conflicts can be avoided. So, this fan algorithm is actually doing that. So, it is progressing with multiple objectives simultaneously, so that it can avoid those future conflicts to a great extent. So, the details of fan is same as the other algorithm, the basic crux of the algorithm we have discussed. Now, apart from these algorithms, the test generation algorithms, there are certain procedures which helps in the test generation process. There are certain techniques that have been introduced into this test generation process, so that this ATPG algorithms, they can be made faster. So, the first one of them in that category is the static logic implication. So, it can help ATPG make better decisions, because it will have the ATPG algorithm will be fed with some information, so that it can take quick decisions on the selecting the inputs to be justified. It avoid conflicts, reduce number of backtracks. So, these are the three outcome if I can do some sort of logic implications calculated. So, we will see what is the logic implication. So, the idea is that what is the effect of asserting a logic value to a gate on other gates in the circuit. So, we randomly pick up one gate and try to see that if I want to set this particular gate point to be equal to 1, then what is the implication on other gates that are there in the circuit. So, other gates in the circuit means some maybe if it is if this output is feeding an OR gate, then irrespective of other inputs to the OR gate, so OR gate output will become equal to 1. So, that way we can figure out certain values for the logic gate outputs whenever a particular gate input or some other gate output is set to be some proper value. So, first we will consider the direct implications. So, direct implications, so this is an example circuit consisting of many inputs, flip flops, etc. Now, you see that if we force this line f to be equal to 1, then what happens? If we force this line f to be equal to 1, then we immediately get d must be 1, e must be 1, g must be 1, j must be 1 and k must be 1. So, if so this computation is done beforehand, that is if I set f to be equal to 1. So, these are the things that are going to happen, these are the different line status that are going to happen. So, how does it help? So, if in my ATPG process, so if it at some point of time we need to set f to be equal to 1, we immediately know some of the other signal lines what are their values. So, whether it gives rise to conflict or not, so that can be checked very easily. So, we do not need to do a simulation for f equal to 1 both in the forward direction and backward direction. Okay. So, these are called direct implication, because by doing one step we can get the implication of it. Direct, similarly, if I say j equal to 0, then its direct implications are h equal to 0, g equal to 0, f equal to 0, w equal to 1, then w should be equal to 1, sorry, this should be x, not w, x is equal to 0 and z equal to 0. So, that will be the implication. So, direct implication for given any signal, if we give it some value, then these are the various are the signal values that will occur. So, we can come to a direct implication for all those signals. So, we do not need to calculate them again at the time of generating the test pattern set. Now, there are some indirect implications as well. So, direct implication, so it is one step. So, basically if we are coming back to the previous example, like when we are computing direct implication for f equal to 1, we find that these are the points. Okay. Now, indirect implications of f equal to 1 are obtained by simulating the direct implication of f equal to 1. So, if we simulate these cases, a d equal to 1, f e equal to 1, g equal to 1, j equal to 1 and k equal to 1, then what will happen? I will get x equal to 1. So, x equal to 1 is the indirect implication. So, which is obtained by when we are simulating this direct implication, because j and g both are j and k both are equal to 1. So, x will be equal to 1. So, this is an indirect implication of f equal to 1. So, indirect implication computation is slightly more complex, because now we have to take all the direct implications and advance those direct implications one step further. So, that is the indirect implication. So, indirect implication, so this direct implication and indirect implication. So, if we repeat this for all nodes in the circuit, so in this case we have shown only for the line f equal to 1. So, if we repeat this process for all nodes like d, e, j, k, w, x, y and z, if we repeat it for all the cases, then for every node we have got idea about what will happen if I set that particular node value to 1 or if I set that particular node value to 0. So, that way it becomes easier in the test generation process. Then there is extended backward implication. So, what it says is we first compute the direct and indirect implications for f equal to 1. So, that is here d equal to 1, e equal to 1 up to x equal to 1. Now, extended backward implications are obtained by enumerating cases of unjustified gates. Like we said that d will be equal to 1, like for setting f equal to 1, one implication is d will be equal to 1, but its inputs a and b, they are still unjustified. So, we can say that this is d equal to 1 is an unjustified case. Okay. So, we need to backtrace further. So, in order to justify this d equal to 1, we will need either a equal to 1 or b equal to 1. So, either of them are required. So, we can say that simulate a equal to 1 with the implication of f equal to 1. So, this is the set S A, okay. And similarly, if we simulate b, the other possibility was a b equal to 1. So, if we simulate b equal to 1 for the implication of f equal to 1, we get the set of gates which is S B. Now, if we take intersection of these two sets S A and S B, then we get that it is the set of extended backward implications for f equal to 1. Okay. So, you will see that if we simulate, so this S A and S B, so A equal to 1, then D equal to 1, then this f is already equal to 1, then all these values becoming equal to 1, ultimately z becomes equal to 0. Similarly, if we simulate S B, that is if we simulate this particular case b equal to 1 for implication f equal to 1, we get the set of symbols S B. So, if you take intersection of S A and S B, we will see that z equal to 0 will come into the thing. So, it means that f equal to 1 sets z to be equal to 0. So, you see that so once we do first we do direct implication, then indirect implication, then we do an extended backward implication. So, that way the almost entire circuit will get covered. So, if there are some possibilities that some of the signal values will get some definite value, so that can be obtained by doing this process. So, this procedure will be repeated for every unjustified gate as well as for every node in the circuit. So, if we do that, then we get a fair idea about what is going to be what is going to happen at various signal nodes, various signal nodes in the circuit when we are putting a particular line to a particular value. That is, this whole thing has happened when we are trying to push f equal to 1. Okay. So, what is the implication of f equal to 1? By doing this process we can figure out. Another implication is known as dynamic logic implication. So, it is similar to static logic implication, but has some signals already assigned values. So, in case of static logic implication, so we were assuming that okay, only the one particular implication like f equal to 1. So, that is known, and rest of the thing we were trying to derive. But in this case we will assume that some signals also have some value, like say suppose c equal to 1 has already been assigned. So, c is already equal to 1, then if we want to get z equal to 0, b must be equal to 0. Okay. So, this is the intersection of having either d equal to 0 or e equal to 0 in the presence of c equal to 1. Okay. So, in the presence of c equal to 1, also in the presence of this c equal to 1 assignment, we are trying to get z equal to 0. So, what is the implication of that? Implication of that says that that b must be equal to 0. So, that way that is a dynamic implication compared to static. Static did not assume any other signal value for any other primary inputs, but in case of dynamic logic implication, so it assumes that some of the input lines have already been assigned. So, in the with respect to that, it is trying to simulate trying to find the implication of some signal line set to some value. Another example, suppose b is equal to d. Okay. So, if we want to propagate this fault effect to z, f must be equal to 1, b equal to d. So, this and so this f must be equal to 1, and if we want to take this further, the intersection of all necessary assignments of all fault effects in the d frontier can be taken. So, we can take this d frontier, like this is a d frontier, then E is a d frontier. So, if we are trying to propagate them, then by setting if we take intersection of them, then this we can find the implication, dynamic implication. Another way of speeding up this fault this test pattern generation process is the evaluation frontiers. So, it says that evaluation frontier is like this. Say for a particular fault Fi, suppose at some point of time we find that these are the this is the evaluation frontier, that is these lines must be set to these values, this point 1, this point d, this point 0, this point 1, this point 0, and for this these are the inputs that have been that needs to be assigned to some value. Now, for the so this has to be forwarded, because for this fault effect this d has to forward to some primary output. Similarly, these 1 zeros they have to be justified and all that. Now, if it is found that two faults have same E frontier with at least one fault effect, then the values on the unassigned primary inputs can be the same. So, this is a result from some paper. So, what it says is that, so if you find that there are two faults having same E frontier, okay, so if it is the same, if for two faults the E frontiers are same, that means we can assign, we do not need to, if we have already computed the primary inputs for the first fault, we do not need to compute primary inputs for the second fault, because for that E frontier the same set of assignments can be done. So, if we maintain the list of if we maintain the list of E frontiers for all the faults that we have processed so far, so whenever we are trying out with a new fault, so and if we see that E frontier is becoming same with some previously computed E frontier, then we can directly take the input assignment part from the first test pattern. Okay. So, that way the process of this test generation may be made faster. Another very important issue in this ATPG algorithm is to identify which faults are untestable. Otherwise, what will happen is, if a fault is untestable, an ATPG algorithm will go on running this backtrack routine and all that. It will try to explore the search space in more and more detail, but since the fault is untestable, so it will never be able to find the particular pattern, any particular pattern for that. So, this is a wastage on the part of the this test generation effort. So, we need to identify the untestable fault. So, if we can do this untestable fault identification fast, then it is going to help us in the test generation process. In fact, any ATPG algorithm you run, so if the circuit has got some untestable fault, it reports that these are the untestable faults in the circuit. So, it definitely does some analysis to figure out what are the untestable faults in the circuit. So, untestable faults are those faults that could not be excited. So, this is one possibility. So, the fault could not be excited, or the fault could not be propagated. Okay. So, basically what happens is, if this is the circuit and there is a fault at this point. Now, one possibility is that the fault is such that I cannot excite this fault. So, this line stuck at 0, I can never put a 1 value at this point. So, due to the logic that it is having, so it is not possible to put a 1 at this point. So, that way it becomes an untestable fault. Another possibility is that it is not possible to take this output, take this observation to some primary output. So, it is not possible to propagate this fault to some primary output. So, this is another case where the fault becomes untestable. Other possibility is that it cannot be simultaneously excited or propagated. So, those faults that could not be simultaneously excited or propagated. So, naturally they are also untestable faults. Now, naturally the problem is that ATPG will spend lot of time trying to generate a test for an untestable fault. So, if we have got a fast identification of untestable faults, so it will allow the ATPG to skip those faults. So, it can avoid those faults and try to generate test pattern for remaining faults. The work by IR 1996. So, that is the FIRE is a tool that has been reported. So, it is based on conflict analysis. So, what it does, let us say S0 is the set of faults that are untestable when signal line S is equal to 0. These faults require S equal to 1 to be detectable. So, when S is equal to 0, so I need to detect the faults, but they will require because we are trying to check for 0. So, we must get a 1 at this line. So, these faults must require S equal to 1 to be detectable. Similarly, S1 is the set of faults that are untestable when signal line S is equal to 1, and these faults will require that S equal to 0 value must be coming for the fault to be detected. Now, if there are some faults which are common in both of these sets S0 and S1. So, the faults which are which become untestable with S equal to 0 may be testable with S equal to 1, and vice versa. The set of faults which are untestable under S is equal to 1 may be testable under S is equal to 0. So, if there is some fault which is common in both the sets, that means it is neither testable with S equal to 0 nor testable with S is equal to 1. So, these faults are simultaneously, so they will require simultaneously S is equal to 1 and S is equal to 0. So, they become untestable faults. So, this is the basic logic by which we compute the set of untestable faults. Like say this one, if we have this line implication of B equal to 1. So, B equal to 1, so it will set B equal to 1, B1 equal to 1, B2 equal to 1, D equal to 1, then X equal to 0 and Z equal to 0. So, this is the implication of B equal to 1. Now, faults which are unexcitable when B equal to 1. So, B equal to 1 the fault, so we cannot check B stuck at 1 because this will require B line to be at 0. Similarly, if we want to check B1 stuck at 1, that is also not possible because I need a 0 at this point, which is not possible. Similarly, B2 stuck at 1, D stuck at 1, X stuck at 0 and Z stuck at 0. So, these faults cannot be excited by when B is equal to 1. Now, because b equal to 1 will you always ensure, we will always make z equal to 0. So, after computing this implication set, you can say that for b equal to 1, all these false lines which are on the implication set, so they become untestable, they are unexcitable. Similarly, we can also find out the faults which are unobservable when b equal to 1. So, that is a equal to 0, a equal to 1, e1 equal to 0, e1 equal to 1. So, this set is the faults that are unobservable. So, naturally, the faults which are undetectable when b equal to 1 is the union of these two sets, the faults that are unexcitable and faults that are unobservable. So, that gives us the faults which are undetectable with b equal to 1. Now, if we consider the other case, that is b equal to 0. So, this is the implication of b equal to 0, b equal to 0, b1 equal to 0, etc. And then faults which are unexcitable when b equal to 0 is basically from this implication set. Faults that are unobservable when b equal to 0. So, if we propagate through the circuit, we will find that c equal to 0 and c stuck at 0 and c stuck at 1. So, these are the two faults that cannot be observed when b is equal to 0. So, if you take union of these two sets, so you will find out the faults which are undetectable when b equal to 0. So, this is the set. Now, we have got the set of faults which are undetectable with b equal to 1 and b equal to 0. So, if we take intersection of these two sets, okay. So, if we take intersection of these two sets, we get b2 stuck at 0, c stuck at 0, c stuck at 1, e stuck at 0, e1 stuck at 0, e2 stuck at 0 and y stuck at 1. So, these are the faults which are common in both the sets b equal to 1 and b equal to 0. So, these faults are actually untestable faults for this circuit. So, you see, for this, even for this small circuit, there are so many faults which are untestable. So, if we have got a big circuit, so you can imagine like how many faults may be untestable. So, if we can detect those untestable faults fast, then naturally we will be able to make our ATPG run faster than in cases where it will try to generate tests for these untestable faults as well.